last time we considered the idea of taking a sum of two orderings. I might have an ordering A with its less than, whatever that might be. I might have another ordering B with its less than. And the idea was that the sum of the two orderings would be, you take a copy of A and you'd follow it with a copy of B. Just like we had the evens, sorry, the other way around, just like we had the evens and then followed by the odds. So that was kind of a simple enough idea. The only thing that little wrinkle that we had was we wanted to make sure that the actual sets A and B were disjoint. So we insisted that when we take sums of orderings, that the field of the two orderings are disjoint, so that then they don't get mixed up with each other. So we'll review that, and then we'll talk about products of orderings. And there, the product of the ordering is, now I should get my hands right for how it looks on the written page. This is the right-hand ordering here. This is the left-hand ordering. So as before, we might have said, looking from your point of view, this ordering came after this one when we did the sum. What we're doing for the product is, what I'm doing is I've got the two orderings, and for each point in the right-hand ordering, I'm going to substitute a copy of the left-hand ordering. So as one of these, it's going to be substituted for this, and for this, and for this, and for this. So I've got, and in the end, I'm going to have this many copies of this ordering. So it's a simple enough idea, and we just have to write that down in a mathematical way. So let's proceed to do that. So just to review some orderings. The sum of two orderings, A with its less than, which I'm calling R, and B with its less than, which I'm calling S, where A and B are disjoint, this was the ordering CT, where C was the union of these two disjoint sets. And for I take any U and V and C, I'm going to define the ordering here as to be UTV, if and only if, well, both U and V are in A, and U comes before V, or U and V are in B, and U comes before V in the S ordering, or U comes from A and V comes from B. So how that looks is like a copy of A followed by a copy of B. And then C is just the whole thing. Now, actually, I've written the orderings out as if they were strict total orderings. Actually, there's nothing in the definition that requires this. These could be partial orderings. These could be like little trees of some kind. In our applications, we're always going to have strict total orderings. So, but I'll just make that comment, which I think is not made in the notes. We don't require AR and BS to be total. Right? That's not actually part of the definition. So, and I gave the example. I said, well, if we have 3 with its ordering here, and then we try and add on, say, omega with its ordering, the idea is simple enough. We have 3 here, and then we have omega. And if you draw this followed by this, actually the whole thing looks just like omega. But if you do it the other way around, omega first, and then follow it by 3, you get an entirely different picture, because this dot has no immediate predecessor, right? Because the omega, from this first omega here, they're increasing here, and then it's just followed by 3 at the end. So these are going to be different. This is called omega plus 3. And this we would say omega, well, it just looks like 3 plus omega. And the little prime on the plus here means this is just our temporary definition of addition. Right? We're going to have a definition of our arithmetic operations by recursion later. To give a formal definition of something like this, I want to make omega and 3 disjoint, and which they aren't at the moment because 3 is a subset of omega. So we had that disjointifying trick. If I wanted to apply the formal definition, I need these fields, these orderings, to be disjoint, to make omega and 3 disjoint. And the idea was, over here, you would use omega cross 0. And here you would use 3 cross singleton 1 with a less than. And then formally, I would make this definition of, what was it, omega plus 3. The t here arising from this was, I put u would come t before v if and only if, well, u equals something of the form k0, and v is of the form, let's say ki, v is of the form mj, and if I equals j, that means they're in the same block. They're either in here or in here. Then 3 alternatives, I equals j, in which case they're in the same block, but k is less than m, or I is 0 and j equals 1, which I can write like this. I don't have to say anything else because the k, then the I things come before the j things. That's it. So I can write this kind of picture definition down like that. Okay. So that kind of reviews what we had for sums of orderings. So unless there are any questions, we'll go on to products. Okay, so again, we'll start out with two orderings. And again, you may want to think of them as being total orderings, right? But they needn't be. So the product, which we'll write AR cross BS, and this is going to be the ordering CU. Now I don't have to worry about disjointness. I'll just take C to be this Cartesian product. Okay, so here this is Cartesian product. And U is, all the jargon might be, this is the reverse dictionary ordering, or the anti-lexicographic ordering. Lexicographic ordering on this Cartesian product. So to specify how that works. We're going to say that x, y, u comes before x prime, y prime. So dictionary ordering, well, the words have only got two things in them. The anti means we start at the back, right? So either y comes before y prime, right, over there in the B ordering, or y equals y prime, and we're in the y prime block here. So we now order according to where the x's lie. So it's like this. Right, so it's easiest to see again through a picture. The picture is we take a copy of the ordering BS, and we replace each point of B by a copy of A. So that's the recipe of how one does this. So examples. I look at 3 times 2. I take a copy of 2 and I replace each point with a copy of 3. So what have I got? Well, obviously I've got 6. And if I reverse this, of course I'm going to have the same thing. This is going to be isomorphic to I take a copy of 3 and I just replace each point here with a copy of 2.
Sorry, please, can you just move the page down a tiny bit, please?
Okay.
Yes, thank you.
Sorry. And this is 3 times 2. Sorry, this is 2 times 3. I take a copy of 3 and I replace each point with a copy of 2. So I in the end up with 6 dots, which of course is just what I had here. But again, you can see what's going to happen with omega. So here's the next example. 3 times omega. I take a copy of omega. I replace each point with a copy of 3. Etc. So actually the whole picture then still just looks like omega, right? It's still got a first element and then it's just repeated successors. So I would say that this here is isomorphic to omega. And now we do it the other way around, and the picture is quite different. I take a copy of 3, and I replace each one with a copy of omega. And that's now quite different. Here we've got 3 infinite blocks, each of which looks like a copy of the naturals. Here we've just got 1 block that looks like a copy of the naturals. So this here is not isomorphic to omega. So we're not going to expect, if our ordinal arithmetic is going to be anything like these pictures, we're not necessarily going to have commutativity. Right? 3 times omega is not omega times 3. Okay, so again, just think of some more examples. We don't have to have natural numbers or ordinals here. The product definition was for any 2 orderings. So let's look at exercise 310. Let's look at Z cross N and Z cross Z. I've omitted the less than here. I mean, it's understood here that this here is the usual less than, and this here is the usual less than. It's just saving space. So what would this look like? Okay, so we keep a cool head. We take a copy of this and replace each point with a copy of the integers. So here's n, which of course is just the same as omega. And now here I copy the integers. So it's looking more complicated. But it's copies of the integers arranged in a omega sequence like that. So what would Z cross Z look like? So here's a copy of Z. And now I've got to replace each one of these with another copy of Z, right? So of course the picture looks so then you might ask, okay, are these isomorphic? And so is Z cross Z isomorphic to Z cross N? So here's Z cross N at the top, and here's Z cross Z down at the bottom. And so how do you approach the question? Well, if you wanted to prove they're isomorphic, you would have to have a bijection between here and here. So one-to-one onto, and it preserves the ordering. So somehow it would be a map from this to here, preserving the dot picture. On the other hand, to show they're not isomorphic, in other words, to say that there is no such map, I can't map the picture dot for dot going across, is you need to pick out some feature of the orderings which is different and which can't be carried over by an order preserving bijection. So, I mean, the approach or method of attack is so if you want to show isomorphism, so obviously you have to provide a bijection F from one to the other, which preserves the order. In either order, it doesn't matter whether which way the bijection goes, from one to the other. In either order, which is order preserving. I mean, you might like to start thinking about whether that's possible with this picture. Or to show it's not an isomorphism, to show there is no isomorphism possible, you want to pick out some feature of the orderings which can't be carried over in an order preserving a way. So one could perhaps pick out some feature of the orderings which cannot be preserved by an order preserving map. I mean, that's just really to restate the question, right? But people often ask and they say, oh, how do I go about showing something like this, right? So, well, I just stare at it and I just see you know, if some bijection comes to mind between here and here, or I look and see, is there some reason why these could never be isomorphic? Well, of course, the difference between these two is the difference between this n and this z. And the n here, right, which is the top picture, the difference here, of course, is that there is a first block, right? There is a first copy of z cross z. And over here, there isn't a first block, right? For any block, there's a block to the left, right? So this gives me an in, a way in. So if I start thinking about this ordering, if I pick any point over here, doesn't matter where it is on here, pick any point on this ordering. And if I pick any smaller point, I can't have an ascending sequence, infinite ascending sequence between here and here, right? There's only finitely many things between here and here. So that's a property of this ordering. I pick any 2 points. I mean, there is a point such that for all smaller points, there is no infinite ascending sequence between them. So that's a property, a statement about the ordering. But over here, that's false. If I pick a point in the ordering here, for example, this one, now that's not true. I could pick a point in an earlier block, and there would be an infinite ascending sequence between these two. I just stick inside this copy of Z. So there is no way that I could map this onto this, because this property of the order couldn't translate over. So the answer here is no, they're not isomorphic, and you just have to write that down. So the solution would be Z cross Z is not isomorphic to Z cross N. Since any point in the least Z block of Z cross N here, since let's say for any point if we take any smaller point, so let me just say, give it a name, K here. If we take any smaller point, L, which comes U before K, in our definition of the product ordering here, then there are only finitely many P, only finitely many points P between L and K. Right, so here's my L and here's my K I'm talking about. Only finitely many P's in between here and here. And that's what goes definitely wrong over here. If this was my L and this was my K, I could have infinitely many in between. But in Z cross Z, if K is in one block, one Z block, and L in an earlier Z block, we should have the collection of P's, which are in between, is infinite. So I couldn't map my L and P in the Z cross Z ordering to an L and P, sorry, an L and K in the Z cross Z ordering to an L and K in the Z cross N ordering. So I found a reason as to why they're not isomorphic.
Sorry, can you just move the page down a little bit again, please?
Sorry, I was getting carried away in my enthusiasm. To an appropriate L of K in Z cross N. So the question, I hope that's all right. I can see a question there. I'm not sure how long it was there. Why isn't the ordering of omega not epsilon? We defined less than on omega to be just epsilon, actually. So that's just how we define less than on the natural numbers, it's epsilon. This was the properties of the epsilon on the natural numbers were that it was a strict total order, indeed a well order, and it corresponds to our usual notion of less than, which we do when we're doing number theory, say. But I can think of this less than as just being a set theoretic relation on the natural numbers. Okay, any queries? So we're going to write, just for a short while anyway, something like alpha times beta for ordinals I'm going to define this to be, well, what ordinal? It's going to be the order type. It's the ordinal isomorphic to, sorry, round bracket here, this product ordering U on alpha cross beta here. I'm going to have gamma delta less than gamma prime delta prime. If and only if, well, gamma and gamma prime come from different blocks. Or they're in the same block, but I've got gamma is less than gamma prime. So again, the order type is, the ordinal isomorphic to the picture. I take a copy of beta, whatever that may be, and I replace each point with a copy of alpha, whatever that is. So I think of it as beta lots of alpha, beta times alpha. So we use multiplication dot there, again with this little prime here. And alpha plus beta with a dot here, again, this is going to be the order type of what I was saying as, well, we disjointify alpha and beta like this, and we put on that ordering which I called T. And I won't write that definition out again. But again, it's the ordinal that corresponds to the picture of alpha followed by a copy of beta. So later we'll define our ordinal plus and our ordinal times by a recursion. But actually, it's, I think, much more vivid to actually use these pictures, right, to get the idea over of what's actually happening first. And our official definitions of plus and times will give us exactly the same outputs, the same results, but they'll be just defined through recursive equations rather than this more intuitive picture fashion. So there's all sorts of fun to be had here, right? 2 times omega, right? So here's omega, and we replace each with a copy of 2. So this is just like the example with 3 earlier. This just looks like omega. So the order type of this picture is omega. So we're going to write this. And we saw that this was different from omega times 2. Actually, I used 3 in the above. Well, here's omega plus omega. But actually, this is just the same as 2 times omega. Well, rather, omega times 2. It's a copy of 2 with each point replaced with a copy of omega. So what we're going to have is, just as for addition, 2 lots of omega is going to be the same as omega times 2. And of course, there's nothing stopping me doing this a little bit further. Right? I can start with omega plus omega here, and I can add on another copy of omega. And I'm going to get that this is just the same as this. I could keep repeating this then through omega times k plus omega. This is just omega times, well, k plus 1. There are also going to be things like omega times omega. So this says take a copy of omega, and I replace each one with a copy of omega. So the pictures are getting bigger and bigger. And later we will call this omega squared, this picture. I can take a copy of omega and replace each point with a copy of the picture above. And I'd call that this here. So there are various things that one can start thinking about. Right? Alpha plus beta plus gamma. Take a copy of the ordering alpha, follow it by beta. Then follow that by gamma. But this is going to be just the same as I take the copy of beta and follow it by gamma. Sorry. And I just add this onto this. Followed by is like an associative operation. So we're going to have some kind of laws coming out like this. And again, we'll establish this when we've defined plus and times by recursion. And then we'll be able to establish associative laws by induction on the ordinals, just as we did for the natural numbers with their well order. But first, we're going to look at just a few more properties of ordinals, abstractly said, before we look at recursion for ordinals. So I'm talking now on page 32, definition 330. Suppose I've got a set of ordinals. I do mean a set, not a proper class. The supremum of A, written sup A. So this is defined to be the least ordinal gamma, so that it's greater than or equal to everything in A. Pick any delta in A, delta is less than or equal to gamma. So it's the least thing greater than or equal to everything in A. We use this once or twice. This will be the strict sup. A little plus up there. This is the same thing, but I put strict less than here. So what is the effect of this definition? So if A has a largest element, and again, remember less than on ordinals is epsilon, just as for natural numbers. So if A's got a largest element, here's A going up the page, and it's mu. Obviously, the supremum is this greatest element, mu. It's the least thing that's greater than or equal to everything here. Sup A equals mu. On the other hand, if you're asking for the strict sup, you want the least thing greater than everything in A. Well, that would be here, mu plus 1. It's the successor of mu. Mu plus 1 here. So that was if A has a largest element. If A doesn't have a largest element, here's A. And now,
Sorry, is there any way you could just put the top of that last page at the top, please? The bottom of that last page at the top.
Okay.
Sorry. Thank you.
Okay.
Thank you. Yep.
If A has no largest element, so there's a set of ordinals. Again, think of A as something like omega, right? No largest integer, no largest natural. Okay, then sup A would be the least thing greater than or equal to all of these elements. But sup A then would not be a member of A because A has no largest element. Right, and I'm not talking about the empty set. If A has no largest element, then sup A is not a member of A, right? But also sup A is the same as sup plus of A. Because this point here, it's both greater than and equal to everything in A, and it's also greater than everything in A. So check your understanding of the definitions by verifying that. So another way of thinking of the strict sup here is strict sup of A is the same as the supremum of all the successors of the things in A. The point is each one of these is bigger than this thing in A. Right? So if I look at the least ordinal that's greater than or equal to all of these, actually it's the least ordinal that's strictly greater than the things in A, which is what this says. Okay, so check that as well. This does have some slightly odd effects. What is the supremum of 3? What is 3? It's a set 0, 1, 2. So supremum says least ordinal greater than or equal to everything in the set. So this is 2. Strict sup of 3, least ordinal bigger than everything in here, it's 3. Don't get confused by the brackets. This set now just has one ordinal in it, 3. Supremum of this set is 3. Strict sup of this set here is 4. Okay, I'm just teasing out the definitions. Supremum of the evens is the same as the strict sup of the evens. And this is just omega. All right, the evens, there's no largest even. Strict sup is the same as the sup. And this is also just the supremum of omega. Okay, so check this definition 330 and that you then understand these things here. And then next time we will proceed with some of these properties of Supremum, definition 332, and so on, and we will look at the recursion theorem for ordinals. Fine. That concludes matters for today. Thank you.